In the last video, we explained the zero and knapsack problem. Let's quickly recap. In this problem, we have a knapsack with a fixed capacity and we have n items each with a weight and a value. The goal is to select items so that the total value is maximized, but the sum of the weights doesn't exceed the capacity of the knapsack. For each item, we can either ignore it or keep it in the knapsack. This gives us a binary choice for each item, so a solution can be represented as a binary string. If a bit is 1, the item is selected. If it is 0, the item is ignored. Now, if we look at all possible combinations of items, we get to the power n solutions. This is a huge number for a large value of n, so exploring all possible combinations can take a lot of time. But the question is, do we have to check all these solutions? Is there a faster way? That's the big question we'll tackle today. If we can't find a clever algorithm that skips unnecessary solutions, we might have to admit that the zero-one knapsack problem is just too hard to solve. In this video, we will use the concept of NP-Completeness to show how challenging this problem is. Time complexity is a way to measure how the runtime of an algorithm grows as the input size increases. We usually express this with big O notation. It tells us the upper bound of the algorithm's running time, so we know how much time it will take as the input gets bigger. For example, searching for an element in an array of n elements takes order of n time. In the worst case, you might have to look at every element. Sorting n elements with bubble sort takes order of n square time in the worst case. Really, we consider an algorithm efficient if it runs in polynomial time. In the case of the zero-one knapsack problem, the exhaustive search approach has a time complexity of order of 2 to the power n, which is exponential. That's not very efficient. The key idea here is that we are not going to directly prove that the zero-one knapsack problem is hard to solve. Instead, we will first prove that the decision version of the zero-one knapsack problem is hard. Once we establish that, we can then conclude that the original zero-one knapsack problem is also hard to solve. So, what exactly is the decision version of the knapsack problem and how does it differ from the optimization version we have seen so far? In the decision version, we are not trying to maximize the value of the items in the knapsack. Instead, we are asking a question that has a yes or no answer. The decision version asks, is there a subset of items that can be placed in the knapsack such that the total weight is less than or equal to the knapsack's capacity and the total value is greater than or equal to some given threshold value? On the other hand, the optimization version, which we saw earlier, is about maximizing something. Specifically, we are maximizing the total value of the items we select for the knapsack. To convert this optimization problem into a decision problem, we need to define a threshold value for the knapsack. Then the decision problem asks whether there is a subset of items that not only fits within the knapsack's weight capacity, but also has a total value greater than or equal to this target value. We can find the solution of optimization version using binary search and solutions of decision version. Let's see how binary search works. We have an array of m elements sorted in increasing order. The elements might not be consecutive. You are given a target value and need to check whether that target exists in the array. Initially, we find the middle element of the array. We compare the target value with the element at the middle index. There are three possible outcomes. If the middle element equals the target, we have found the value. If the target is smaller than the middle element, the target must lie in the left half of the array. If the target is larger than the middle element, the target must lie in the right half of the array. We discard the half of the array where the target cannot be and repeat the process on the remaining half. With each step, you cut the search space in half, which makes binary search extremely efficient. Now, let's connect this idea back to our optimization problem. For the optimization version of zero-one knapsack problem, the range of possible optimal solutions is between 0 and the total value of all items. In the worst case, no items are selected, giving a total value of 0. In the best case, all items are selected, giving a total value of all items. Let's define L equals 0 and H equals total value. We know that the optimal solution lies between L and H. Now we can apply binary search to narrow down the possible optimal values. We set the target value t to the middle of the range. We solve the decision version of the knapsack problem for this target or threshold value t. If the answer is yes, it means the optimal solution is between t and h. So we set L equals t. If the answer is no, it means the optimal solution is between L and t minus 1. So we set h equals t minus 1. We repeat the process until L equals h, at which we found the optimal solution. Time complexity of this process is order of log of sum of value of all items, which is polynomial. We can say if there exists an efficient algorithm for decision version of knapsack problem, an efficient algorithm can be designed for optimization version of the knapsack problem. A verification algorithm checks whether a proposed solution is valid for the decision version of the knapsack problem. If we can show that the verification algorithm runs in polynomial time, it will be useful for our purpose. In the decision version of the knapsack problem, a solution can be represented as an n-bit string. Each bit corresponds to an item. A bit set to 1 means the item is included in the knapsack. A bit set to 0 means the item is not included. Let's try to write verification algorithm for decision version of knapsack problem. We initialize two variables, t value equals 0, it stores total value of the selected items, and t weight equals 0, it stores total weight of the selected items. Then we loop through each item I from 1 to n. If the corresponding bit xi is 1, it means the item I is selected. We add the item's value vi to t value. We also add the item's weight wi to t weight. After the loop, if t value is greater than or equal to the target value or threshold value and t weight is less than or equal to the knapsack capacity, it means answer is yes. Otherwise, the answer is no. For any given solution, we can verify whether the solution is valid or invalid. And good thing with this algorithm is that its complexity is polynomial. We can conclude that the proposed solution for the decision version of the knapsack problem can be verified in polynomial time. In general, NP problems are those for which a proposed solution can be verified in polynomial time. Therefore, decision version of the knapsack problem is also a NP problem. A decision problem P is said to be reducible to another decision problem Q in polynomial time if there exists a function f that transforms an instance of P into an instance of Q while preserving the answer. In other words, for every yes instance of P, there is a corresponding yes instance of Q, and similarly for no instances. The symbol represents polynomial time reducibility and shows the hardness relationship between two problems. In this context, P is polynomial reducible in Q means that problem P is at most as hard as problem Q. In other words, Q is at least as hard as P. If we can solve Q in polynomial time, then we can also solve P in polynomial time by transforming P into Q in polynomial time. NP-complete problem P must satisfy two conditions. First one is P belongs to NP. This means P is a problem for which a solution can be verified in polynomial time. Second one is every problem Q in NP can be reduced to P in polynomial time. In simpler terms, a problem P is NP-complete if P is a problem in NP and it is as difficult or hard than any other problem in NP. We have already shown that the decision version of the 0-1 knapsack problem is in NP because it has a polynomial time verification algorithm. This satisfies the first condition. But to prove that knapsack is NP complete, we need to show it also satisfies the second condition. That is, every problem in NP can be reduced to the decision version of knapsack if in polynomial time. Demonstrating this directly for all NP problems would be very time consuming and difficult. However, there is a trick. Yes, there is a trick. Assume an NP-complete problem X that we already know is NP-complete. From this, we know that every problem in NP can be reduced to X in polynomial time. Now, if we can show that x can be reduced to the decision version of knapsack in polynomial time, we can use the transitive property of polynomial time reductions. This would mean that every problem in NP can also be reduced to the decision version of knapsack in polynomial time. In summary, our goal is to find a NP-complete problem x which is polynomial time reducible to decision version of knapsack. The good news is that there is an already known NP-complete problem, the subset sum problem, that can be reduced to the decision version of the 0-1 knapsack problem in polynomial time. By demonstrating this reduction, we can conclude that the decision version of the 0-1 knapsack problem is NP-complete. Let's briefly discuss the subset sum problem. Given a finite set of integers s and a target sum t, the question is whether there exists a subset of s such that the sum of the integers in that subset equals to t. Our goal is to take an instance of the subset sum problem and reduce it to an instance of the decision version of the 0-1 knapsack problem. We create an instance of the subset sum problem. We create a set S of n integers and a target sum t. We create an instance of the decision version of the 0-1 knapsack problem. We create a set S dash of n items. For each item I, set both the weight wi equals ai and the value vi equals ai. We set the target or threshold value t. We set the knapsack's weight capacity to t. Now the question is, if there is a yes instance in the subset sum problem, does the corresponding instance in the 0-1 knapsack problem also have a yes solution and vice versa? Let's answer the question. Since in this reduction the weight of each item is equal to its value, the constraints in the knapsack problem, sum of weights less than equal to t and sum of values greater than equal to t, are only satisfied with the sum of subsets integers equals t. Therefore, if there is a solution to the subset sum problem, there will be a solution to the corresponding 0-1 knapsack problem and vice versa. It means we have successfully reduced the subset sum problem into the decision version of the 0-1 knapsack problem. Now, we have to see whether this reduction takes polynomial time. Now the question is whether the reduction is polynomial time computable. We need to analyze the time it takes to convert an instance of the subset sum problem into an instance of the decision version of the 0-1 knapsack problem. What's given? A set S of n integers and a target sum t. How we construct the knapsack instance? First, for each item I, we set both the weight wi equals ai and the value vi equals ai. Time complexity of this is order of n. Then we set the threshold and knapsack's weight capacity to t, which takes constant time. The total time complexity for the reduction is order of n, which is linear time. Since linear time is a subset of polynomial time, we can conclude that this reduction is polynomial time reducible. We can conclude that the subset sum problem can be reduced to the decision version of the 0-1 knapsack problem in polynomial time. Since the subset sum problem is NP-complete, we can now conclude that the decision version of the 0-1 knapsack problem is also NP-complete. You might think that since decision version of 0-1 knapsack is NP-complete, it must mean that no polynomial time algorithm exists for it. The answer is no. We have not proven that no polynomial time algorithm exists for decision version of 0-1 knapsack. Despite extensive efforts by mathematicians and computer scientists, no such proof exists to date. So why did we spend all this time? We didn't waste our time. Rather, we have shown that the decision version of 0-1 knapsack problem is at least as hard as other NP-complete problems, which is already considered hard by many scientists and academicians. This was the main objective of the reduction. The conclusion is that decision version of 0-1 knapsack problem is hard to solve, and therefore optimization version or our original 0-1 knapsack problem is hard to solve. In the next video, we will see how greedy algorithms can be helpful in finding the near optimal solution in polynomial time. Thanks for watching. Don't forget to like, share, and subscribe so you never miss what's coming next.